So folks, today's lesson will continue our discussion of limits. We're gonna discuss about limits that are infinite, which are also important. We did not do any of that earlier. We are going to address how limits. We more or less talked about that, but I want to go back and address how limits are recognized on a graph. And finally, we are going to do some, the applications to this notion of limits. The plan for the week, for the remainder of the week, we're going to discuss continuity. Tomorrow, we're going to discuss. So we're going to discuss the rigorous definition of limit. I would call that the French formalism, which would be will take us maybe another day or so, or half a day or so, because we won't spend too much time there. And once we move on, we are ready to actually start derivatives. So towards the end of the week, or hopefully, or for sure early next week, we are going to discuss derivatives. So this week, our goal is to finish up this limit and continuity section and move on to derivatives as soon as possible. All right. Without any further additions, I'm just going to pull up a screen here. So that will be the whiteboard. And I'm going to share that with you folks. Right now, you should be able to see the whiteboard. So what happens, I'm going to do, as I said, I like to do problems from the book to, exemplify the notions that we cover here. And the first problem that I'm gonna do today is question number 29. So that will be number 29 of section 1.5. All right, so this was a practice problem for I think I included that as a practice problem. Of course, it's in the homework, it was for the quiz as well. I did not assign a question like that, but here's what it is. So it says here, the limit as x goes to 5 plus of x plus 1 divided by x minus 5. So we're going to calculate this limit. And here's some things to notice. As you can see here, 5 plus means, and I remind you, means x can only be here in this problem. X can only be greater than 5, but it's going down to 5. So we can say x is approaching 5 from above. That's what's most textbooks that I've seen use this notation because it's slightly more intuitive than this kind of abstract with a plus in exponent. But the idea is x is approaching 5 from above, which means x is a number like 5.1, 5.01, maybe 5.001, and things like that. And then we are interested in the values of this particular function here, which I'm going to call f of x, and I'm going to share another screen with you. So I'm going to do this problem again, like we usually do these problems when we need computations. We'll do them with Desmos. So I'm going to start up Desmos here. I'm going to stop sharing this screen with you, and I will share a new screen where I'm going to show you Desmos. Now, Desmos, of course, is not pulled up here. It's our school's webpage. So we're going to go to desmos.com, and then we go. There's Desmos there, and I'm going to have a graphing, pull up the graphing calculator, and the graphing calculator again. Let's remember. So we're going to put a note to ourselves here first. So we're going to say we calculate limit as x approaches 5 from above or from the right side, right? So above means we're going down to 5. From the right side, numbers on the x line going towards 5. All right, so approach, okay, of the function. And I'm going to say the function here was x minus x plus 1, looking at the function here, x plus 1 divided by x minus 5. So unfortunately, this doesn't allow me to write the function nicely because I'm typesetting here basically. But you get the idea. So there we go. We use parentheses just like that. And then over here, we're going to do the calculation. So first of all, let's give this function a name. Again, I always like to keep things organized. Say f of x equals, and I'm going to say that thing x plus 1 divided by x minus 5. There we go. That is my function. So it appears here on the screen. It's this hyperbola here. The point of this thing is that we want to make a table of values and we want to figure out what happens when x approaches 5 with the values of this function. So we're going to pull a table here. I am pressing the plus sign. Folks, I want you to be familiar with these procedures. Again, I don't want you to discover them on the time at the time when you take a test. So do practice at home, kind of the things that I do here. You want to redo that at home. Make sure that you yourself are able to do these things. So I'm going to place a t here. Remember, I told you the reason why we put a t there is because this program doesn't like the same name of a variable, and I'm putting t and f of t here. So there we go. So we got the value that we want to give to t, and we said that we start with 5. Now, if we do 5, oh, that's a bad idea. So no, you don't want to be at 5. So you want to be away from 5, going towards 5. So let's say 5.1, let's say. That's going to give you a value of 61. And if you do 5.01, that's going to give a value of 601. And if you do 5.001, that's going to give you a value of 6001. And if you do 5.00001, I'm going to put, how many zeros did I put here? 1, 2, 3, 4. 4 zeros. Oh, look at that. So you get these numbers here. So look at this. On the left side, I want everybody to look carefully here. Again, on the left side, we have these numbers going very, very close to 5. But look what happens on the right side. I get 61, 600, 6,000, 600,000. Essentially, you can even ignore that one if you want. It's not so important in this case. So what do you think, folks? What would the natural answer be for this limit here? So what do you think the natural answer would be? You can answer in the chat or open up your mic and say it loudly here so everybody can hear, folks. What do you think the answer would be? All right, so the answer would be infinity. Very good, Joe. So we got an answer that's infinity. Yes, infinity. We are looking at that here. So folks, when the numbers really go very, very high like that, what happens with a point on the graph? Let's look on the graph here. So now I cannot see because my graph is covered by some other screen. All right, there we go. So that's the reason why I'm moving the graph here. But let's see what happens with a point on the graph. Look here, folks. So my point on the graph, I'm approaching. Remember, you wanna keep an eye here on the left coordinate of this number, which is a number on the x line. And look at 723, now 695, 654, 632, and so on, and it becomes very, very small, close to 5. Look at that, 588, and so on. So that number really gets closer to 5, but look what happens with the y coordinate. The y coordinate goes higher and higher, and the closer you get to 5, the higher you get with the higher coordinate. In fact, I need to zoom out to be able to see what happens with, let's say we put a coordinate here, 539. Look at that, there's 16. And if I zoom in even more, so let's zoom in even more. So look at this. So I put the number here, 522, I'm at 28, 517, 516, I'm at 37, and so on. So you're getting very, very close to 5 with a x coordinate, but the y coordinate goes to infinity. So that's why we say that this limit is infinity. So we're going to write that. I'm going to stop sharing here. So 1 second, I'm going to stop the share. All right, so we're going to write that on our whiteboard here. And we're going to say, oh, this limit, we just found this limit to be infinity. So we're going to save that. All right. So some limits, you see, folks, some limits could be infinity. So is it possible that the limits from both sides are equal to infinity? Yes, it is possible. So it is possible that limits from both sides are equal to infinity. I will give you an example. Example. When the limit as x approaches, let's say, let's say 5 plus of something, some formula here. I'll design a formula here for this to work, is equal to the limit as x approaches 5 minus. Now since I put going down here, let's not put going down, let's put going straight to 5 plus. So it still means limit as x approaches 5 from the right, and here, okay, from the left, the same expression. I want these to be both equal to infinity. Well, what expression could I put here? For example, folks, if you put this 1 over x squared minus 25. Now, this formula will have a limit of infinity from both sides when you approach. One second here. No, not this one. Hang on a second. Let's change the formula. Nope, wrong formula. So this one will not have that limit that I claimed. Let's do this formula, x minus 5 squared. Apologize, folks. This one will have limit infinity when you approach from both sides. Let's see that that is the case. So if we put this formula in both formulas here, we'll have a limit of infinity from both sides. And I'm going to stop sharing this with you. I'll pull back decimals. All right, so let's pull back decimals. And let's calculate the limit as x approaches 5, not of this function. I'm going to change my notation here. So the advantage of working with this software is that it really you can just change. You can do the calculations for one function, and you can just change the formula, and you get automatically the calculations for another function. So in my case, I'm just going to say 1 over here x in my notes. Oops, I put the wrong thing. X minus 5 squared. I'm going to put that there, and I'm going to do the exact same thing with the formula here. So I'm going to put the 1 there, and I'm going to say here at the bottom. Come on. All right, so that's going to work. 1 second here, folks, to put this thing. At the bottom, I'm going to have x minus. Oh, look at that. So as you can see, these numbers are very large, and when you approach from both sides, look what happens. So I'm going to zoom in a little bit. Oops, zoom in the wrong way. Okay, I'm going to zoom in a little bit. So you see these numbers get closer and closer to 5 from both sides, but the values are going higher and higher on the graph. It goes all the way up to infinity. And you can check this thing with a table. So you can do another table if you are curious from the left. This is the exact same table. Actually, let's do it because it takes really just a minute here. So we can put another letter here. Let's put A. And let's put f of A on this side of the table. F of A. Oops, not that. A. And let's put over here. Let's put numbers close to 5, but from the left. So we say numbers like 4.9. And over here, even closer to 5 will be 4.99, for example. And over here, even closer to 5, 4.999, and so on and so forth. And if you put 4.999999, a bunch of nines, you get 10 to the 12. So how many nines do I have here? 1, 2, 3, 4, 5, 6. You get 10 to the 12 here. So that's a very large number. As you can see, in both cases, the limit from both sides is infinity. So we say that in this case, since the limits are equal according to our definition from both sides, they're equal to the same, value, infinity in this case, we're going to say that the limit exists at that number and is infinity. Now in the book though, whenever they find limits that are infinity or possibly negative infinity, so if you want a negative infinity situation, all you have to do is to put a -1 here at the top, and you'll get a limit that goes to negative infinity. So the whole thing flips down. All right, so if the limit is infinity or negative infinity, just remember this point. In the book, they say the limit does not exist. So I disagree with that definition. Now it depends which book you look at. In my class, folks, here, when the limit is infinity, just say it exists and is infinity. So does not exist would be when there's various values, possibly infinity and some constant values or some other things. But when there's a situation that's clear, crystal clear like that, the limit is infinity from both sides, we're going to say that it exists and is infinity. All right. So that is the first point that I wanted to make today, limits that become infinity. All right, so now what else do we have here today? So the second thing that I want to point out today is how to work with graphs. Now, of course, it's important to figure out, and you have a bunch of problems in your book, and I'll pull up one of the problems here. So I don't know if you can see here in my okay. So I have a book here. All right, so I'm going to put that in front of the camera, and you can see a bunch of problems here. It's unimportant. It's unimportant what their numbers are, because I'll draw the pictures, but just to show you here. So these things need to be addressed as well. So I'm looking at numbers like, and let's start with a number like 4, and let's figure out what the limits are on the graph. So on the graph, we said that I'm going to draw the picture here, folks. So don't panic. So if you don't have a book with you, you can still see what the problem is. But I recommend that you have a book next to you so you can actually look in the book. So what I'm going to do here, I'm going to share with you the whiteboard. And on the whiteboard, I am going to do a drawing. And the drawing will be the one from, okay, so 1 second. All right, so 1 second, folks. I'm on page 2, and I want to do problem 4. So that will be problem 4 from section 1.5. Now, folks, if you have any questions, please don't hesitate to interrupt me. I'm going to draw a picture here so everybody can see it. It's not so easy to do it by just putting, the picture in front of the camera. And this one is not so easy to draw on Desmos Cyber. So I'm just going to point out that in the book, they tell you that there's a point at 2,3 here. And this is a full dot. This point is 2,3. And then there's a curve that goes, something like this. Something like that. Or maybe not exactly, but kind of, you get the idea. There's a curve. So this is my graph. And then there's another point here at this one, and this one is open, is 2,1. And from this point, there's a branch of my graph that goes to, what is this, 4,4? All right, so 4 would be about here. This would be about 2, okay? So 4 would be about here, and 4,4 would be over here. Now, this is an open point, again, like the one earlier. Okay. All right, so 1 second, folks. There's a bunch of things here appearing on my screen. All right, so this would be the point 4,4, and my graph, would go something like that. All right, and then the graph goes down from 4,4, and actually it goes a little higher, and it goes somehow, down like this, somewhere. All right, and there are a bunch of questions. So this is my graph, this is my function, y equals f of x. And there's a bunch of questions, and we're going to answer those questions right now. The limit as x goes to, And it says here 2 minus of f of x. And let everybody, so pay attention here. I'm explaining how to figure this out on the graph. So what we learned up to this point was, and I'm gonna point this out because it's very important. Up to this point, we basically have this algebraic approach. So we had algebraic some formulas for f, and then we use a numerical approach to plug in values, plug in numbers, and estimate what the numbers were on the graph, and then figure out the limit by looking at where the values go. And we did the graphical formula, but we never ran into a situation, at least up to this point, we never ran into a situation where only the graph was given and nothing else. No formula, no values for f, nothing really. Just a couple of things there, a sketch, basically. So this is the first time when we encounter this situation. And you will encounter this sometimes. And again, I told you, this is a situation that appears quite frequently in practice where, for example, people, a doctor, let's say, or when a doctor looks at your chart of I don't know, the sugar level in your blood, or the I don't know, the heart, the blood pressure, or something like that. So the doctor looks at the general shape of a graph. Of course, they will look in detail afterwards at the details. So let's see, on this day, the sugar level was this much. On another day, the sugar level was this much, and stuff like that. But they also need this general shape. So this is kind of the thing that we do here. We look at the general shape. Of course, we know some values there, but we estimate the limit. So we kind of make an estimate what the limit will be at 2 in this case. So the limit at 2 means really, folks, limit as x approaches 2 from the left side. So we're going to go towards 2 this way with x. Now, if x approaches 2 from the left side, then you can go up here on the graph, and where is it that your point is on the graph? Oh, it's over here. So you get this point here on the graph, and I'm going to color this point, and I'm going to color it with a different color. So how about I color it with options? All right. Oh, there we go. I'm going to color it with a different color. I'm going to color it with, all right, with red. So oops. Sorry, folks. Oops. I don't want the eraser. Oh, okay. I'm going to color it with red here. So this is my point here, my red point. And this point, as x approaches 2, so you see I'm approaching 2 from the left side. My red point, goes like this, slide like this on the graph, and it approaches this one here, the one at 2, 3. So we're going to say, folks, and I'm going to go back to write with black on the screen. We're going to say that the limit as x approaches 2 minus from f of x. So if you look at the point on the graph slides towards 2, 3. But remember that the limit is always read on the y-axis, the y value. So I'm reading the second value here, which is 3. So that's why this limit is 3, folks. And I hope everybody understood this example, because I'm going to ask you to do a bunch of questions here. So for example, what is the limit, part B, the limit as x approaches 2 plus of f of x? What is this limit, folks? So let's see. Let me know in the chat. So when I approach x from the right, like that, right? So we use from the right. When x approaches from the right, what is the value of f of x as I approach 2 with x? So you can tell me in the chat, folks. Let me know what's happening. All right, so what is the limit from the right, folks, of f of x? Anyone? Let's see. So there was an answer. Let's see. Somebody said 1. Okay, why is it 1? So let's see. Yes, indeed, it is 1. So let's color that again with red. So here's where my point is. When x is here on the right, my point is somewhere on the graph here. Somewhere here maybe, right? And I'm going down like this as I'm sliding towards 2 with x, this point on the graph slides and it goes like this and it goes closer and closer to this one here at 2 comma 1. So I'm reading, folks, I'm reading the y value of that point, and the y value is indeed, so the limit as x approaches, uh, I already wrote that, just gonna say 1 over here. So that is the y value of that point. So it is indeed 1. All right, folks. Now, this being said, I'm gonna mark this like that, gonna mark it nicely, and that's the limit as x approaches 2 from the right. And now we can do limits as x approaches 2. So the limit as x approaches 2, does anybody know what that would be, folks? Of f of x, what is this number here as x approaches 2? Let's see, anybody, you can say in the chat, folks. What do you think the limit when x approaches 2 is? I'm trying to see if you paid attention here, the problems that we discussed up to this point. Let's see. All right, anybody here? All right, so there's a comment. Does not exist. Does not exist. Yes, yes, yes. Very good, very good. So okay. So you got it, folks. You got it. It does not exist. So the limit does not exist, and that's because the two limits from the left and from the right are not equal. The reason is limits from left and right are not equal. So yes, 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 there we go. The limit does not exist. All right, very good, folks. So this practically finishes our problem. I can now answer quickly the remaining ones. The value of f at 2, we already had a problem like that on the quiz. So what do? We look above 2 and we look where the full dot is, and the full dot is here at 2 comma 3. So I'm going to say that the value at 2 is 3. All right, not this one here, the empty dot, it means that's missing, right? And then you can answer part E, and part E also is asking for the limit as x approaches 4. All right, limit as x approaches 4 of f of x. Now, what is 4? 4 would be someplace here. There we go. I see. So that's the reason why I mark it on the graph. There is 4 here. Let me erase this previous stuff. All right, folks. So at 4, as you can see, there's a missing value, but not a problem. Not a problem, because as you approach, delete this stuff from here. All right. Oops. Can I undo that? I think I'm just going to have to draw it again. There we go. All right. So as I approach, folks, as I'm approaching 4 from both sides, this way and this way, my points on the graph will either way slide toward this 4 comma 4. So even though the value at 4 is missing, the limit as x approaches 4 of f of x will end up being 4. That's the y value here at this point, 4 comma 4. So again, folks, the story with limits is a story of the neighborhood. So it doesn't matter. So imagine that you have a house to estimate. You are a real estate agent. You have a house to estimate in a neighborhood. And, maybe the house was not built yet, or it's not accessible. There's no data on the house. So what you do, you're going in the neighborhood and you look at the map and you say, oh, I know how to estimate this one house and this one house and this one house and this one house. And these houses are all in that neighborhood, are very close to the house I'm looking for. But what's important there, I know what the values of these houses are. So even if the house that I'm looking at, the value is missing, I can estimate that as a limit. So if every house in this neighborhood costs 100,000 or approximately 100,000, then it's a fair conclusion to me that, the house there that's in the middle of the neighborhood, whose value I don't know, it would be also 100,000. So the limit is a story of a neighborhood, not so even if you don't know what happens there, if a value is missing for whatever reason, like it happens in this case, 4,4. So this is a good example. It's important to understand that the limit will still be 4, the limit. Yep. So the value at 4 does not exist, but the limit is there. All right, so that's exactly what part F is asking us to say what the value of 4 is. And I'm going to say here does not exist. According to my graph, there's no value at 4. So I'm hoping that this is a good example, folks, for everybody, and everybody understood it, because this is the most basic, and everything on the test and such from this point on the next test, you will get questions like this. I'll give you a graph and I'll ask you what's the limit from the left, from the right, this and that. So you will have to figure out yourself by just making an inspection of the graph. So that being said, I encourage you to do problems like 5 and 6 and 7 and so on. So I encourage you to do those on your own at home. There's a bunch of problems, good problems there. I am going to do problem 8 next. Problem 8 is slightly different, not so much in terms of content, but in terms of what is required. So the result, the outcome is slightly different. That's the whole point. All right. So let's see what's happening with problem 4. All right, folks. The problem that we're looking at here, okay, so there we go. So let's share with you again. There we go. So the problem that I want is this 8 of section 1.5, and you will see that the outcome is slightly different here. So I'm going to look in the book again. I just have to copy that graph because it's a bit too complex for me to do it, on Desmos. So we have this line at -3. -3 will be over here. All right, let's say, and we have this vertical line. And my graph is really close to, it's kind of going like that at -3. And then as you move past -3, you're gonna cross the graph somewhere, and then you're gonna go down. Oops. So you're gonna go down. Sorry about that, folks. Not a very good sketch here. So there's I should draw another line here at what number is this? This would be -1 here. So you're going to go down like this, kind of like that. And then you're going to go down again on the other side, and you're going to end up at 2, which would be, let's say 2 would be here. So draw another vertical line just to kind of anchor my graph, folks, because this is a bit of a complex problem. I mean, it's harder to draw than the actual problem. So the actual problem is not so difficult, as you will see. And finally, we have this one. Kind of like that. And there's a bunch of questions. And we're going to address all those questions here. So first of all, let's see part A. What is the limit? The limit as x goes to -3 of a of x. By the way, this function is called y equals a of x. You really could give whichever whichever names you like to this function. Limit as x goes to -3. So this is an interesting question. So pay attention, it's not asking you free exponent minus or anything like that. It's asking you the number -3. So there's no exponents there, which means it's asking for the overall limit at -3. So from the left and from the right. So let's look from the left. So if we go from the left like this and we approach -3 is over here. Let's do that with red. So let's say we go this way towards -3. What's happening with my point on the graph will be somewhere here. It'll go up, 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 up. It'll keep going up forever. So the limit from the left, folks, is -infinity. And then if I do the exact same thing, remember -3 is here, if I do the exact same thing from the right, then I'm looking at a point maybe somewhere here on the graph, but then as I approach -3, this point is also going to go like this, and look at that. So it's going up, 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 and it's approaching infinity from both sides. So the limit as x approaches -3, as x goes to -3, is positive infinity, folks. Very important here. So again, make sure positive infinity. So both sides of the graph go towards infinity. All right. Now, let's see what else is there. The limit as x for part B, the limit as x goes to 2 minus. So part B, let me change the colors here. So part B, the limit as x goes to 2 minus of a of x is equal to, and let's see, what is this equal to, part B? So for part B, what is 2 minus, folks? So now remember, this is not -2, it's 2 exponent minus, which means limit. So just to clarify notation, it really means x approaches 2 from the left of a of x. So there's some other books, again, really, I really don't know why the author of this book insisted on using this kind of abstract notation, because you could say clearly here, x approaches 2 from the left. If you want, you can write on the test like that. It's not a mistake, folks. By the way, there's other books that use actually this notation instead of this one. So as you approach 2 is here, and you approach it from the left side. So you're going like that to 2. Let me change colors quickly here. So it means that your point on the graph will be on this side, and as you approach 2, you are going to go down, 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 down towards -infinity. So this is going to be here -infinity, folks. The limit as x approaches 2 from the left side. All right. Part C, and you guessed what part C would be. Part C would be the limit as x approaches 2 from the right side. And that will be a of x, and this is going to be equal to, and the values, again, so we're looking at the right side of 2. Let me change colors here quickly. So I'm approaching 2 like that from the right side. Where is the graph here? The graph is over here. I have a point here, red on the graph. And as I approach 2 with x, my point is sliding up towards infinity. So the value of the limit is positive infinity. And you can see now, you guessed that the limit at 2 does not exist. Because look here, we have a positive infinity and we have a negative infinity from the 2 sides. But there's no question about that. So, okay, so we skip that question. So we can say here, let's say C prime, the limit as x approaches 2 of a of x does not exist. You can say here does not exist, or we can say DNE, right? For short, as most people say that. And finally, part D, let me change back to black again. Part D over here, the limit as x approaches -1 of f of x. So let's see, where is -1? -1 will be here on the x-axis. Now, if I approach -1 from both sides, this way and this way, what happens here? So the values of my function, now we're going to go down on the left side, from the left side. So we're going to go down like this, but also from the right side, we're going to go down. So the values of this limit are both equal to, and I'm going to say here, -infinity. So that is the limit as x approaches -1. It does exist, in fact, there, according to our convention that if the two limits are equal at a point, we're going to say that value of the common value of those two limits is, the limit. All right, folks. So what you see here in the book, in the remaining exercises, is a bunch of applications. And I want you all to go through all these assigned problems, try them at home, and finish up these applications. And next time, which is tomorrow, we are going to discuss the laws of limits. So in contrast with what we do today, tomorrow we are going to discuss about some rules for limits defined algebraically. So we're going to calculate limits. Of course, we're still going to look at graphs, but we're going to continue algebraically. That is, with some algebraic manipulations that allow us to calculate limits easily. We are done for today. If you have any questions, folks, I'm gonna close the recording here. The recording, so that the file doesn't become too big.